very happy to have the Professor Willie Penn today for the joint colloquium. So let me introduce the Professor Willie Penn before his talk. So the Professor Willie Penn is the, as you know, the world-renowned theoretical cosmologist. Has been working on the wide variety of the topics, so ranging from the cosmic string, topological defects, also cosmic baryons and dark matters, using the Sunyaku-Chodovich effects, gravitational lensing, and more recently on the cosmic reionization physical processes, and also the MHD simulations. So Professor Willie Penn was the NTU undergraduate in the mathematics. He obtained his PhD from the Princeton University in 1995. And he was a Harvard University Junior Fellow before his joining the faculty at the University of Toronto and the Canadian Institute of the Theoretical Astrophysics, known as CTP, in 1998. So he is currently a Canadian Institute for Advanced Research Senior Fellow and also the Associate Director of the CTP. So recently his research has been focused on the cosmological applications of the hydrogen 21cm line. It's a very hot topic in the observation cosmology, and also the pulsar scattering phenomena. So today, the Professor Penn will talk about his observational and also theoretical work on the fast radio bursts, FRBs. FRBs are recently discovered sub-arc second radio transient phenomena, and whose physical origins are yet unknown. And it's a very exciting field here. So today, and also recently, his observation work has been also published in Nature. And today, Professor Willie Penn will discuss this very exciting result. Let's welcome Professor Penn.
Thank you. Always nice to be back at IAMS, where Katie said I was a student here a number of years ago. Always good to see universities getting more and more advanced, more interesting. So I very much enjoy coming here. I'm going to talk today about something that I am not an expert in, so we never thought that we would ever write a paper on this until a few months ago, until we found an event, and we will hear the story of how this happened. This is a very new field, so in that sense, there are no experts. These things really became accepted as being real maybe 2 years ago. The first events were claimed maybe 10 years ago. But initially it was very doubtful if these things really were from the sky or if there were some non-reproducible interference phenomenon from the Earth. So in the last few months, though, there have been a number of new developments by various groups around the world, and I think this is an interesting time because right now we are starting to get the first hints about some of the physical properties, and hopefully in the next few years we will find out what they really are. It is not that often in astronomy, at least, that a phenomenon goes from not being believed to be real to actually resolving what it is. So this is, I think, an interesting time, and we're right now in the middle of it. So we get to hear part of the puzzle. The picture here is the telescope with which we found this serendipitously, with a GRE word, that we took data for a different purpose, and then we ended up discovering one of these bursts in our data, so we started learning about it. And in fact, the timing is very nice, and I wouldn't have been allowed to give this talk even 1 month ago. This paper was embargoed until December 3rd, so this is probably the first talk that I'm aware of that is allowed to actually talk about the sites that we've been discovering in this particular study, and go a little bit overviewing what other information is also known. It's a large collaboration, not because any of us ever had thought of studying fast radio bursts, but because the Green Bank 21 centimeter experiment is a fairly extended collaboration, including a number of people here in Taiwan at National Taiwan University, at ASIAA, at Zhongshan Daxue here. So we have, a collaboration here and across the world, and some of these people are listed here. I think and sitting at ASIAA, we're all part of that team, and then developed this new discovery. I'm going to start this. You first see the first item I put on here is Toronto, and I'm going to use this in the good old tradition in movies. At the beginning, you always have some advertising. I'm going to start off with some advertising and then explain what the science is about. Here's an advertising. I did not get any money from the Toronto Visitor Office or Tourist Office or anything to put this up, but quite the contrary, this is an image out of our recent paper, 1507. So this is a paper out of an astronomical publication. It's meant to, on one hand, show how nice Toronto is. Who here has been in Toronto? Oh, yes. Great. And then those of you who have not been, this is a picture taken. Toronto has an island. The city is along a lake, and the island separates the mainland by the Toronto harbor. Harbors are built to prevent waves from the outside from entering and disturbing the ships. So you get a very peaceful water surface on the inside. And this paper, in fact, this phenomenon, we think is actually related to fast radio bursts. I'm not going to have much time to go into it. But the thing to note is that when you have a light, and you look at it in a slightly perturbed surface, okay? If you had no surface of the lake at all, you would see exactly one image of everything on shore. That's just a mirror. When you have a few waves, all these images get extended into a line. Remember that. This is something I'm sure you've all seen, and there's a whole paper about why this happens and how this relates to various phenomena that you'll hear about in fast radio bursts. This paper was written before we knew about fast radio bursts, but before I knew about them. But it's the same phenomenon applies. Toronto, I want to advertise more than just the nice view and the city lights. I'm going to advertise that, according to National Taiwan University, a very reliable source of information, Toronto is ranked the #3 university in the world in terms of research impact. So I want to encourage any students here or anyone interested in research to think about applying to Toronto, applying about doing studies there, doing postdocs there, doing anything in Toronto. In fact, I just read in the Toronto News that the dean was in Taiwan a few weeks ago, and that in fact some of the alumni, actually there are very few students from Taiwan who go to study at the University of Toronto. But there are those that do have been, some of them have been very successful. For example, all of you may know, and raise your hand if you don't know who Liu Zhaoxuan is. You don't know him. He was the Premier of Taiwan fairly recently. And of course, his connection is that he's got a PhD in chemistry from the University of Toronto. So if anybody wants to become Premier of Taiwan, come to Toronto first. So it's, advertising, I figured, and that was my 2 minutes worth. Back to the radio. So in the radio waves, there is a phenomenon called plasma dispersion. The way that works is that if you have any source in the sky coming towards the Earth, the short frequency, the blue, meaning the short frequency radiation, travels at close to the speed of light, and then the longer the wavelengths, the more slowly it travels, and below a plasma frequency it just cannot propagate at all. Okay, so you get a frequency-dependent delay. This is a big problem for anyone who uses GPS, for example, because the propagation time from the satellites to your phone depends on the weather and other things, on the electrons, on this delay. This delay there is different every day and every hour. So there's a lot of, people spend millions of dollars trying to figure out how to get rid of this, how to compensate for this phenomenon to make your GPS work more accurately. So without, this is important for us in everyday life. Now, astronomically, because the signal travels through many more electrons than just the satellites, this becomes quite a noticeable effect. And I'm going to start just with the main picture of this discovery paper. That what you see in the sky in this phenomenon called fast radio burst is in the radio frequency, that's 700 megahertz to 900 megahertz. This is kind of the frequencies where you used to have TV and where you used to have mobile phones. There's still some mobile phones left in this band. That in this band you get propagation through space, and you have this black line that was detected on this event happened on May 23rd, 2011, so about four and a half years ago. We recorded this event. We didn't know about it at the time. And the phenomenon is that the low frequencies arrive, a few seconds later than the higher frequencies. This white outline is the fit to a lambda squared dispersion, which is characteristic of this plasma dispersion. And you can see, and we'll quantify this later, that this indeed follows this law very nicely. There are two gaps in here which are due to what's called a receiver resonance, a very technical issue with the telescope that you cannot observe on those two bands. And the rest, most of the granularity you see is just thermal noise. But at the end of the day, so these kinds of events, there have been maybe 20, there are about 20 of them known today. They last maybe a millisecond, so they're very short, and they're dispersed, and they have a fair amount of energy. I'm going to get back to that in numbers in a few minutes. But that's the basic phenomenon that people are trying to understand. What is this? Where did they come from? Why are they dispersed? These dispersion measures, the units that are usually used is parsecs per centimeter cubed. If you multiply it out, it's some number of electrons per centimeter squared of column. That's the duration. I've mentioned most of these. I'll come back to some of these properties. I'm going to start off with, one interpretation that has been made is that these electrons are just the electrons in our universe. And then you can ask, how far away does the source have to be for that dispersion be due? The further away you are, the more electrons you have between the source and us. How far away do you have to be to explain these dispersion measures? And the answer is typically you have to be at a redshift of order 1, so halfway across the universe is how far they would have to come if that is the origin, and that's being the most fashionable interpretation of that is that in fact the dispersion relation is caused by the cosmic electrons. So you get a distance that way. You get a size by saying, well, a millisecond. So just by causality, light can travel about 300 kilometers in 1 millisecond. Speed of light. Can't go further than that. So for something to be as short, so normally we say for something to be short in duration, these regions have to be causally connected. So the emission region is probably no bigger than 300 kilometers in size. If you know the size, and you know the distance, and you know the apparent temperature brightness, notice that we measure this to be a few Kelvin. The antenna temperature is measured in Kelvin on Earth. You take the inverse square law to the source, and you get a temperature at the source which is 10 to the 36 Kelvin. Okay, reality is equivalent. You have to be a bit careful of what it means. Another unit that's popular is Planck temperatures. This is 10,000 times higher than the Planck temperature, and that is the metric that some people use to say that fast radio bursts are the brightest event in the universe, because presumably then that was, unless there was some higher than Planck period, which who knows. But this would be the highest known brightness temperature of any event in our universe. I'm not going to go into all these caveats. So that's a mystery. How do you generate such intense sources of electromagnetic fields? In fact, it raises all kinds of issues. An electric field of this strength will generate Schwinger production of electron pairs. The vacuum will break down. Bad things will happen if this in such a process. And in fact, it's been speculated what happens. So that's part of the mystery, that this very strong electric field is interesting. It's a type of physics that has never been observed, and it's even difficult to imagine how you would even think about calculating something in that regime. Okay, when the vacuum is no longer the vacuum at these energies. That's part of the interest of why there's been a lot of discussion on what these are. We don't know what they are. I'm going to start, take a step back about the types of things people discuss. Okay, this is an incomplete sampling, but I'm going to classify them into different types of things by a classification, not a physical one, but just conceptually. You can have sources that are what we call cataclysmic, meaning they happen once and can never repeat. For example, it's been proposed that these things might be exploding, Hawking primordial black holes. Okay, if you have a small black hole at the beginning of the universe and it evaporates, the final explosion, who knows what happens, but maybe it looks like that. Nobody knows how to calculate Planck physics, but energies are right. The energy scales would work out. Okay, that's one type of explanation. Of course, those will never repeat. A black hole can only explode once. The opposite type is something called a blitzer, is if you have, say, a neutron star that is too massive to be stable, but maybe it's stabilized temporarily because it's rotating rapidly. If you rotate fast enough, you can counter gravity for a while, and as you slow down, you will form a black hole. And this process of forming a black hole, maybe something complicated will happen, and that is called a blitzer. Whatever that is, that would happen. Not that anybody knows how to calculate it, but at least there's a lot of energy available if you were to do that. And again, that's cataclysmic because it can only happen once in the life cycle of such a process. It can never repeat. When you form a black hole, it's not going to happen again. And then there is everything in between, merging neutron stars. And these are all what I call cataclysmic types of sources. They never repeat. They're quite spectacular, whatever it is. And maybe that's what they are. Then there's a category of more perhaps mundane candidates that have been proposed. That would be processes that are transient, but in principle at least, could repeat. And perhaps we want to include something called magnetar flares. Magnetars are pulsars, neutron stars with very strong magnetic field that are actually known to exist. So the magnets are known to exist, they're known to have flares. It is not known what a flare would look like at the low energy in the radio, but who knows? It's been proposed that it could be a planet orbiting a neutron star. It's been proposed that it could be just a very strong pulse from an isolated neutron star. And these are all things that are related, that at least could repeat. And many of these things that are known, they are known to be neutron stars which have planets, they are known to be neutron stars which have flares. So each of these things is known to exist, but none of them, of the ones that are known, have enough energy or enough brightness temperature to explain what we see, but you never know. Maybe there's some class of objects far away that is different, that's similar, but it's different and much more energetic, that explains these phenomena. And then there's the more what I call local explanations, meaning not, those have been things that are within our galaxy that might be causing it, that have been proposed. There was a amusing paper earlier this year that microwave ovens apparently have a magnetron running at 2.4 gigahertz, and when you open the door, there's a safety mechanism that the power shuts off so you don't get fried by the microwaves. But apparently when you turn the power off on a magnetron, the remaining inductive current and keeps emission going for a millisecond, and then the frequency drops because the power is dropping, just like an FRB. So it's known that opening a microwave near the telescope, of course, then the energy is very small. You probably only get a milliwatt coming out, but for a telescope, of course, that's a lot of energy. So that's a mechanism that's known to look similar. It's thought not to be the case, actually. Some events called peritons are in fact microwave orbits, but it is thought that others, like the one we showed, is not. Other phenomena that are more local and perhaps more mundane are called flare stars. That the sun has solar flares, magnetic fields that may put out radio emission as well. So that's another kind of phenomenon that we propose. So what's interesting about them? Why? I think Nicole asked me a few minutes ago, why would anyone care about any of these? Well, obviously the energy densities are very high, and energy means the electric field densities have to be very, very high. So it's a new regime that has never been experimentally observed or tested. So when the vacuum breaks down, what actually happens is something that would be amusing to be able to measure. Beyond that, it has been thought, has been proposed, maybe these are useful as cosmological yardsticks, that you can measure distances, you can measure how many electrons there are. Maybe it works, maybe it doesn't, because of course, if you want to measure it accurately to 1%, which is what would make it interesting to understand, say, dark energy, then you would have to understand the 1% effect from the local host galaxy, so that's not clear that that would work. There's been, I think, the nicest paper on the subject is by Matt McQuinn, where he really goes through all the things you could learn about the electrons in our universe if you were to measure enough radio bursts. And that's again a separate subject that could be of interest cosmologically. And I think still the main thing that's interesting is that it's a new coherent field phenomenon that we otherwise don't have access to. So we had a paper earlier this year. It's always good to write a paper predicting an effect whose answer you actually know. So after we detected the fast radio bursts, we had we had more information than anyone else had. So it's time to write a theory paper predicting certain phenomena, knowing that these predictions are going to come true. That's a simple way of making predictions that are then verified in the future. So this is one of these papers where we post-predict the phenomenon. By the way, the paper is very honest about it. It says that we make predictions based on things that only the authors have access to. Where we in fact classify the types of sources that have been in discussion, ranging from cosmological ones, and I think I've gone through so many of them, and predictions they make of things you could measure about them. Okay, so I think now the exercise is, in this very wide range of things that they could possibly be, how do you tell? What kind of measurements do you have to make to get closer to the answer? And obviously finding more of them is nice, but how many do you need to find? And what would you have to see about a large number that would distinguish them? If they're all the same, whether you have 1 or 1,000, it's not clear what you learn. And so we classified the various types of things that is a signature, but that we think distinguishes them. Scintillation. I'm going to get back to that. That's related to the very first picture of Toronto that I showed. There is the luminosity distribution. Okay, so luminosities, meaning for every bright one, how many faint ones should I see? If they are extragalactic, meaning not in our galaxy, then they should be roughly isotropic. And of course, the further they are, the fainter they are, but there are more of them. The number goes up as distance cubed. The flux goes down as distance 1 over distance squared. The number count goes as flux to the -3 halves. Okay, so if you look 100 times fainter, you'll see 1,000 times more events. That's the Euclidean count law. That's prediction. So so if you were able to measure this law, right now with 20 it's hard to measure, but if you were able to measure this dependence, you could tell that it's at least uniformly distributed in the Euclidean space. If you're cosmological, then it could be different. Okay, so if you measure it to be different from that, then you know it is not Euclidean, and maybe it's because it's at the it's cosmological effects or something else is happening. Now, of course, that being different doesn't tell you what the answer is, but at least this you can falsify, and this one criteria what you would have to measure. And the magnetic fields, I'm going to get to that. That's something that we know more about. You can try to find counterparts. Now, many of them have no counterparts. So again, if you saw something, that's very good. You might learn something about the source. If you find nothing, you may, again, all of these, I think none of them have a definitive prediction. I think finding nothing is consistent with all of them. Just because none of these things are so predictive that you say, oh, I will see exactly this flux at this other wave band. Most of them you just don't know. So seeing nothing tells you nothing. Seeing something will tell you something. And then you can try to speculate on the ranges. Going back to our favorite, my favorite radio burst, because we discovered it, of course, it must be our favorite. It's the date we have. It was taken as part of a 21 centimeter survey that was of some interest in the past as well. And here we have a double discovery on the same data set, which is always good. You only need to take the data once. You get two discoveries for the price of one. And it's good that I think both of these projects were projects which were kind of against the odds, meaning most people thought this would never work. Okay, in both of these cases, people said, it's a waste of telescope time, and even more so, even a waste of the people. Even if the telescope costs nothing, it's a waste of my time, of my students' times, to try this, because it will fail. You will find nothing. It will never work. And sometimes you have to be able to assess, what the issues are, and sometimes you just have to do it anyways, even if people don't think that this would be doable. And there are various challenges for both of these about why people didn't think this would be possible, but it is. I'm going to jump into a phenomenon called polarization. This burst is unique, that it's the first one for which we measured linear polarization. In linear polarized light, when it passes through a magnetized plasma, rotates its apparent polarization direction in a frequency-dependent way. So when a light comes in with a vertical electric field, after propagating through, again I'm going to use a technical term, it's circular polarization by refringence. What that word means is that the left and right circular polarization travel at different speeds. And a linear polarized light is a decomposition of the two, and as they move at different speeds, then the angle will change. And the reason for that is because the electrons in a magnetic field travel and have different energy dynamics rotating against and with the magnetic field. So what you get is splitting of energy levels of the electrons that leads to birefringence, and that is something that is observed in this in our fast radio burst. So this is the total intensity, and here are the polarization Q and U, and you can see a frequency-dependent lambda squared oscillation of the apparent electric field vector, which tells you that the light propagated through a magnetized medium, magnetized plasma. That is measured fairly accurately. We will measure a rotation measure. There should be units on this, radians per meter squared. And we measure it to be, it's a number. Is the number big or small, or why is it interesting? Minus 186.19 plus or minus 1.4, so that's measured very accurately. Is it large or small? Well, compared to what you expect for this line of sight, the prediction for this line of sight based on nearby quasars is 18 plus or minus 3. Okay? So this tells you that the magnetic field is not due to the intergalactic medium. People used to think that would be the primary source, but it is now known to not be the case. So the magnetic field, and it cannot be in our galaxy either, because the